Hey, it's Mr. K doing a video for AP Physics 2. This is a magnetism video. We're going to do a little bit of an introduction to magnetism and see how far we can get before I get bored or say, hey, the video's too long and stop it. But anyway, let's start off with this bar magnet. And a bar magnet is going to be made up of all these little magnetic domains. And usually with a bar magnet, you'd say that one side is north, the other side is south. But what actually happens here is you've got all these little domains in there with their own individual north-south poles. Because if you take a bar magnet and you broke it in half, you'd have two magnets with north-south individually. So if I were to cut this one in half, I'd have a north side over here, a south side there, a north side with a south side over there. And that's just because all these little magnetic domains have their own individual directions to them, magnetic field vectors for those individual magnetic dipoles. There is no magnetic monopole. In other words, there's no just one north pole. There's always a south pole that is attached to it. And these could be arranged in all these different directions. And if we're in class, and I would have already showed you something with probably a iron nail, and you hit it and you put it in the vicinity of a magnetic field, and you can actually magnetize that sucker. So the idea here is that these magnetic fields, these little magnetic domains, they could be all randomized, but if they have a general net direction, then what you get is a magnet. And so one easy way to do that is to put a some kind of ferrous material, some iron-like material inside of a strong magnetic field, and then you hit it. And when you hit it, you kind of jar these magnetic domains to where the vectors are coerced to go in one certain direction. And then you can remove it from that strong magnetic field, and then there you go, you have a magnet, or at least a temporary magnet. So we're going to talk about magnetic fields, and the north side is going to have that magnetic field go out, and the south side is going to have the magnetic field go in. So you should have out and in there. It's another thing that I would have showed you in class. And these magnetic field lines should be complete. There should be no break in them. So with magnetism, just remember that your magnets have a north pole and a south pole. The north pole is going to be where those magnetic field lines come out. The south pole is going to be where those magnetic field lines go in. And let's go ahead and also talk about the right hand rule, which we should know from angular momentum. But what we can do is we can say, all right, there is this phenomena where if you have a moving line of charge, in other words, some current, and we're going to talk about the flow of positive charge there. If you have a flow of charge, and it's positive charge, and let's say it's moving upwards, then all around this wire, you're going to have magnetic field. And so that magnetic field, the way you figure that out, is you take your right hand, and you put your thumb like this, as if you were going to hitchhike in a certain direction. And your thumb is going to point in the direction of the current. So in this case, it's going to point up. And your fingers are going to be curling around in only one direction. There's only one possible way that they can curl around if you're using your right hand rule, or your right hand. And so with that wire, let's say my pen is that wire, if the current's going up this way, I'm going to put my thumb in that direction. My finger's going to curl around it. And no matter which way I orient that wire or that direction of charge, my fingers are always curling around in that certain direction. So for this one, the magnetic field lines are going to be all around it, but they're going to be circular, and they're going to radiate outwards radially. So put my thumb up, I'm going to curl my fingers around, which means that this magnetic field is going to be coming around. Let me use a different color for that. It's going to be coming around kind of like this in front of the wire and then going back behind it. And it's going to be going around in that direction. So again, take that pen, hold it, just practice it, put your thumb in that direction, curl your fingers around, and as you can see, my fingers are curling around to the right in front, and in the back they'll be curling around and going to the left. Try to make that kind of a three-dimensional image for you. So this will get weaker as you get farther out. Probably not the best drawing. And so as you get farther and farther and farther away from that wire, it's going to get weaker and weaker and weaker and weaker. The magnetic field formula for a straight wire is going to be B is your magnetic field symbol. It's going to be a vector. and that's going to equal mu naught, which is the permeability of free space. You're going to find that on your equation sheet. This is going to be I divided by 2 pi r. And some of you might be wondering why there's not a square on that. Well, that would, usually from like a point charge or a point mass, you would have an inverse square law where you get weaker to the inverse square. This one's going to be a line of charge, so that kind of starts to cancel it out. So if you were talking about individual ones, yeah, you might get a square there, but because you have a line of moving charge, those field vectors from individual moving charges start to cancel out, and you reduce in magnitude by a rate of just 1 over r. So something useful for that is it's you have not just one wire, but let's say you have 2 wires. And if we have 2 wires here, both with current going upwards, what we can talk about is, well, what's going to happen to these 2 wires? So if the current's going up, I is going up, works the same way. Put your thumb in that upwards direction, curl it around, and you've got those same coming around the front to the right, going around in the back to the left kind of magnetic fields. Well, what's going to happen to these 2 wires here? You can talk about you just placed 1 wire in the vicinity of this wire's magnetic field. And if we were to continue around with our fingers, I'm going to go into the board or into the page for this other one's magnetic field lines. I wonder if I can use this. Should have drawn these green, but whatever. So the magnetic field from this side is creating field at this location into the page. And we're going to denote into the page by drawing circles with X's on it. And again, these are from this wire on the left side. Likewise, this wire is creating magnetic field out of the page at the location of this other wire. Okay, so into the page on the right side, this moving charge is going upwards. It's in a magnetic field created by this wire. It's being affected by the magnetic field. You can't affect yourself with your own magnetic field. Just doesn't work like that. And so what's going on with this charge? The first right-hand rule is the one where you put your thumb in the direction of the moving charge. You curl your fingers around. That's going to be how that magnetic field is going to be pointed, and no matter where you are. And my iPad just froze. No, there's. The other right-hand rule is the right-hand rule for the force on a moving charge in a magnetic field. Well, take your right hand, put it out like this, okay, just like that. And there's another one that kind of looks like this that I'm not too fond of because you kind of forget what's going on. So I like this one better. Open palm right-hand rule. So your thumb is going to stick directly to the left. Your fingers are directly 90 degrees to that, and then there's your palm. So each of these is going to have a use for us. So again, your thumb is going to be the direction of your moving charge. In this case, it's going to be straight upwards. All right. Your fingers, since there are many of them, are going to be the direction of the magnetic field vector that we're currently in. So right now, thumb's going up. Magnetic field on the right side is going into the page. And then that leaves one option for my palm. And if you're doing this with me, your palm is going to be pointed to the left, which means that, hey, your palm, that's what causes forces. And so your palm is going to be the direction of the force. So your thumb is going to be the direction of the charge, moving charge, upwards. Your fingers are the direction of the field that they're in, into the page. And your palm is going to be the direction of the force, which means that this wire is going to be pulled in this direction by some magnetic force due to the moving charges that are moving in the magnetic field of the other wire, from the other wire. Likewise, this one, my field is going towards us, so my fingers are going to point towards us. It's going to be kind of hard to do it in camera. My thumb is going to point upwards, and if that's the case, force it, then my palm points to the right. And so I'm going to have some kind of force, magnetic force, that's going to be pulling or pushing this wire on the left side to the right. So these two wires are actually going to be drawn together. And that's kind of weird that your moving positive charges are going to be drawn together. But it happens all over the place. And if you've ever watched a lightning storm, you know, the only reason why that lightning is able to converge on and go down as a bolt is due to this effect where you have these moving charges all moving together, and they're all attracting each other. At the same time, they're repelling each other due to the Coulomb's force, but they are able to move in a line and be drawn to each other as they create this magnetic field that pulls the other ones towards them. All right. So, just as a practice, we have the first right-hand rule and the second right-hand rule, and let's see what we can do with that. So, let's give ourselves a region of space that has magnetic field going towards us. And again, the reason why it's a dot with a circle, imagine like you're being shot at with an arrow. If you're being shot at with an arrow, you see a dot with a circle around it. It's a point. If you're shooting the arrow, then you're going to see a X, like the fletching. So, different ways to draw your vectors into and out of the page. So let's say that our magnetic field, our B field, is going at us. It's coming straight out of the page. And we're going to have a charge here, and we're going to call this charge a positive charge. And it's just going to be sitting there. And so if you have a charge that's positive sitting in a magnetic field, the question that you're going to have to answer for yourself is, what happens to it? And the answer is nothing. Absolutely nothing. So the equation for force on a charge in a magnetic field is Q VB. And we need to make sure that these are all, that these two things, the velocity vector and the magnetic field vector, we need to make sure that those are perpendicular to each other so that it actually does obey our right-hand rule. Q is going to be the amount of charge. So the more charge you have moving, the more force is going to be on it. It also depends on the velocity of it and the magnetic field strength. So if this charge is just sitting here, I don't care. It's just not going to do anything. You know, the big misconception coming from 6th grade or something like that is like, if you have a magnetic field, oh, the charges, they must be doing something. No, it's not, they don't have to be doing anything. All right, now if they move, now we have some kind of thing to think about. So let's say that this charge was moving, I don't want to write right now, let's say this charge is moving down, okay? So this charge is moving down, what would happen to it? You're going to take your right hand, you're going to line your remember your thumb is the direction of motion of the charge. That's going to be going straight down. I shouldn't have chose down. And then your fingers are going to go in the direction of the field. It's coming out towards the camera. And so I'm going to have a force on this charge that's going to be pointed to the left. If I say, let's say this charge is moving to the right. If this charge is moving to the right, I've got my thumb in that direction. My fingers are going to be pointed straight up again towards the camera. And I have force downwards in this direction on this moving charge that would have been moving to the right. Now, what if this charge was moving straight into the camera? What if it was moving straight up? Well, my thumb would be going up, and my fingers would be going up too, and that breaks the right-hand rule. And so we would have no force there. And so what you got to make sure you do is you got to find whatever component, if any, of velocity is perpendicular to the magnetic field. And usually that's going to rely on you using sine, but depending upon the angle that you're given, could be cosine. So I don't want to write down sine or cosine there. In college, you're probably going to see a sine. But just make sure they're perpendicular. So just say, all right, one last try. What if this charge was moving in that direction? So that is the velocity of the charge. If it's moving in that direction, there we go. Open right hand rule. Oh gosh, gotta tilt my hand, and yep, we got a force on it in that direction. There's your force. And what this is gonna cause is charges to move in circular paths, because if you notice, the force is 90 degrees to the velocity vector, and whenever forces are 90 degrees to your velocity vector, it causes you to turn. Alright, those are centripetal forces. You might have charges that have some component that might not be perpendicular, and it's going to cause your charge to spiral. Alright, so magnetic fields, very simple at the moment. We will talk about induction and flux and all that other great stuff in another video, because I think this one will be good enough with just those two things. Right hand rule, remember, you got first one, closed right hand rule. Take your thumb, point it in the direction of the moving charge. Your finger's going to wrap around, and that would be the direction of the field that that charge is creating. Other right hand rule, open hand. Again, your thumb is in the direction of the moving charge, but then now your fingers are in the direction of the field that they are in. Not the field they're creating, but the field that they're actually in. So these two wires would give a force that would be pointed towards each other and pull each other together, which, as a last note, yeah, if you were thinking, what if they were going the other way? What if we had one with downwards current and the other one with upwards current? What would that do? And if we had downwards and upwards current, well, this downwards current, thumbs down, curl your fingers around, and by the time we get over here, our field that the left one's creating is going to be out of the page, opposite of what was going on over here. And look, if we do our other right hand rule, the open one, my charges are going up. Ah, crap, not again. My hand's gonna break. My field's going towards you, and my force is going to the right. And so the force would be going to the right. Now, if I talked about the right hand side wire, it's creating magnetic field too. Take your thumb, close right hand rule, thumbs up, curl them around. It's coming out of the page over here, just like it was on the other side. And now take your open right hand rule, thumbs down it, out of the page, your force is going to the left. And if your force is going to the left, these two wires separate. Alright, that'll be the end for the video. We'll make another one coming up shortly.